Hello, everyone. My name is Skylar Rodriguez, a current biochem student at UT Austin. As I said last time, this month we'll be focusing on the fundamentals of chemistry. Before we get to the nitty-gritty, there are still several topics to cover, such as understanding the difference between accuracy and precision, classification of matter, extensive and intensive properties, physical and chemical properties, and lastly, significant figures. We're going to start with accuracy versus precision and how it is implemented in chemistry. Accuracy refers to the agreement of a value with a true value. Precision refers to the agreement between several points of the same quantity. Accuracy is important as it ensures calculations reflect real-world chemical properties. This can be applied to checking if a scale is properly calibrated. An inaccurate scale would not give a correct value, possibly skewing your experiment and data. Precision allows us to confirm experimental methods by giving us consistent results over time. A good example of this, do you want to take a medication that only works 50% of the time or 90% of the time? I would personally want to take a more precise medication. Here is a visual representation for you all. There are four targets. The first one is both accurate and precise. The second is low accuracy, high precision. Notice that the holes are not in the center. They are all tightly grouped, but they are all tightly grouped. The third is accurate and precise on average, but the points are scattered. The last target has poor accuracy and precision, showing the holes to be all over the place without hitting the target. Now we're going to go into a different classifications of matter. Matter is anything that has mass and takes up space by having volume. Different examples of matter are solids, liquids, gases, and plasma. Plasma, if you don't know, is a superheated gas that can conduct electricity. The atoms in plasma bounce so violently that they rip their own electrons off, creating a highly energized soup of free-floating electrons and positively charged ions. You might not know this, or maybe you do, but fluorescent light bulbs happen to have plasma in them, and that's how they work. Energy forces and concepts such as thoughts, time, memories, and emotions are not matter. In order to classify matter, we have to split into two main groups, pure substances and mixtures. Pure substances break into two more groups, elements and compounds. Elements are the simplest form of matter. They are made of only one type of atom and cannot be broken down further by chemical means. Compounds, on the other hand, are made of two or more different elements chemically bonded together in a fixed ratio. Compounds can be separated by breaking chemical bonds. And here are some written definitions. Go a little slow here. All right. Mixtures consist of two or more substances physically mixed, but not chemically bonded. Each substance keeps its own individual properties, and you can separate them by physical means such as filtering or boiling. Mixtures then go into two other groups, homogeneous and heterogeneous. And that's a little layout of the full diagram. Let's go back up over here. Homogeneous mixtures look perfectly uniform throughout. They are blended so evenly that you cannot see the individual parts with the naked eye. Examples of homogeneous mixtures are air, salt water, and even brass. Heterogeneous mixtures are not uniform. They can be easily seen as different parts, phases, or layers. An example is fruit salad, where you have a clear distinction between the different fruits. Next is understanding what exactly extensive and intensive properties are. Extensive properties are physical traits that change when the amount of matter in a sample changes. They depend directly on the size or quantity of the substance present. Examples of extensive properties can be mass, volume, weight, size, total energy, enthalpy, which is total heat content of a system, heat capacity, the amount of heat energy required to raise the temperature of the entire sample by 1 degree, and number of moles. Don't worry about the scary words that I just said right now, such as enthalpy and heat capacity. We'll go over them eventually, but only once we start tackling thermochemistry. Then we have intensive properties, which are physical traits that remain the same regardless of the amount of matter. These are intrinsic characteristics that depend solely on the identity and type of substance it is, not its size. Examples of intensive properties are density, melting point, boiling point, specific heat capacity, molar mass, state of matter, which is solid, liquid, gas, color slash luster, and hardness and malleability. Okay, let's try a question. What are some intensive and extensive properties of 2 liters of water? I'm going to give you a couple of seconds to do it on your own, and then I'll explain. Okay, some answers you could have written for intensive properties could have been that the density is 1 gram per centimeter cubed. It has a melting point of 0 degrees Celsius, a boiling point of 100 degrees Celsius, a molar mass of 18.015 grams per mole, or that it's in a liquid state. For extensive properties, you could have said that it has a volume of 2 liters and a mass of 2,000 grams. Physical and chemical properties are used to describe how matter behaves under different conditions, distinguished by whether observing them changes the identity of the substance. Physical properties are characteristics that can be observed or measured without changing the chemical composition of the substance. This includes melting and boiling point, density, solubility, which is how well solute dissolves in a solvent, where the solute is the substance that gets dissolved, and the solvent is the substance that does the dissolving. So think of this as solute being salt and the solvent being the water. Um, then state of matter and conductivity of heat or electricity. Chemical properties describe a substance's ability to undergo a specific chemical change, forming an entirely new substance. This can be observed during a chemical reaction. Examples of this range from flammability, reactivity with acid, toxicity, oxidation, to heat of combustion. And let's go all the way up. Physical and chemical properties act as identifiers to distinguish different elements and compounds. This is important to know. Now, there are several ways to describe matter as it transitions from one physical state to another. Here's a diagram to see the different ways. Solid to gas is called sublimation. Gas to solid is deposition. Solid to liquid is melting. Liquid to solid is freezing. Liquid to gas is vaporization. Gas to liquid is condensation. Gas to plasma is ionization. And plasma to gas is deionization. Lastly, we are discussing the significant figures, also known as sig figs. Significant figures reflect the precision of a measurement. When working with sig figs, there are rules for counting them in a single measurement and rules for calculating with them. The first rule is non-zero digits are always significant. Here we have 145.8. Since there are no zeros, we can just count the digits of the number, which come out to 4 sig figs. The second rule, zeros between non-zero digits are significant and are known as captive zeros. Say we have a number 2008. Because there are captive zeros, there are 4 sig figs. With 5.002, there are 2 captive zeros, making it 4 sig figs. Rule 3. Leading zeros or zeros with before the first non-zero digit are never significant. They only act as placeholders. With the number 0.0025, it might be tempting to count this as 5 sig figs. But because 3 zeros are leading before the 25, it is 2 sig figs. Try with 0.0501. How many sig figs are there? Let me give you a second. All right. There are 3 sig figs. We don't count the 2 leading zeros, but count 501. Rule 4. Trailing zeros that at the end of a number are significant only if a decimal point is explicitly present. For example, 120.00 has 5 sig figs, 2 sig figs from the non-zero digits, and 3 from the trailing zeros that have a decimal. 1200 or 1200 with a single decimal at the very end has 4, 2 from the non-zero digits and 2 from the trailing zeros. Now, let's look at 1200 or 1200 with no decimal point. It only has 2 sig figs as the zeros are not considered significant without an explicit decimal point. Lastly, rule number 5. Exact numbers have an infinite number of sig figs. We all know 12 inches equals 1 foot because it has an exact conversion. It has an infinite number of sig figs. Defined conversion factors and counted objects have infinite sig figs. In order to incorporate multiplication division into sig figs, the final answer must match the fewest number of total significant figures in any of the original numbers. Here, we're multiplying 4.56, which has 3 sig figs, by 1.4, which only has 2. The product comes out to 6.384. But we have to follow the rule and change it to 6.4 since the second original number had 2 sig figs. Addition and subtraction final answers must match the fewest number of decimal places, or least precise column, in any of the original numbers. 12.11 has 2 decimal places, plus 0.3, which is 1 decimal place, equals to 12.41. But because 12.4, but becomes 12.4, excuse me, since there was 1 decimal place in the original equation. You all have successfully made it through your second chemistry video. Pat yourself on the back. It's a lot of information to go through, so expect these videos to be kind of hammered in. I will link practice problems to make sure you all can apply what you have learned in this video. In the next video, I will be discussing concentration terms, a quick history of chemical laws, the periodic table and periodic trends, what the atom is, isotopes, cations and anions, and electromagnetic radiation equations. I stay safe. Hope you all do well, and I'll see you on the next one.